is rather familiar. So first, I'm thinking about a two-dimensional lattice. I will take a specific finite box inside. My box, it will be convenient to start them from minus n plus 1 and end at n. Okay, so this is the point n comma n. And in the center, I have the special vertex 0, 0, which I will sometimes denote by 0 bar. And what is a random surface? A random surface is a function from this box. I will take it also with periodic boundary conditions, so it's actually a torus. So I have a function from the vertices of this box to the real numbers. You may think even of a matrix sometime, a function. And I'd like to sample this function like that. I will have one normalization. My function will be, I will take the value 0 at the middle vertex 0, and then it will be sampled with the following probability density. The density of phi equals 1 over z, some normalization factor, e to the minus sum over all edges in my torus of some function u applied to the difference of phi along the edge, phi v minus phi w, like so. And let me already tell you one particular example, which is the most familiar one. If you take u of x to be x squared, then your density becomes 1 over z e to the minus sum over all edges of the gradient along the edge squared. And this is the most familiar example of this kind. This is called the Gaussian free field, or more precisely, the discrete Gaussian free field. And what is the idea behind this construction? Well, the idea is that you should think of this as a sort of height function. Maybe the membrane which separates two different phases of matter. Maybe you think that something is very smooth, very flat, but actually it has some microscopic fluctuations, and you want a model for these very miniature fluctuations. So your model says that different values, adjacent values, do not differ by too much. Not deterministically, but rather stochastically. You penalize the how much they can differ with this density. You give this square penalty, for instance. But more generally, you may consider some potential, so-called potential function u, which will penalize in a different manner the gradients. Let me also mention the one-dimensional model. If you do the same thing on a one-dimensional grid like that, and we say without periodic boundary conditions, then you can normalize your function to start here. And then, by this definition, you will get actually a Markov chain. The two-dimensional model is not Markovian. It has the domain Markov property. Here, you will actually get a Markov chain. So it will be a random walk of sorts with the increments distributed according to this potential. In the case of x squared, the increments will be Gaussian. So random walks we understand very well. And in particular, we know that there is universality for random walks. If I take a random walk from 0 to n, many of the properties are the same regardless of what distribution the increments have. And in fact, one expects such a picture also in 2 dimensions. So one expects that there will be some universal properties of these height functions which are independent of the potential, at least when n is large and maybe up to constants. They will only require some small details of the potential, like second moment or something like that. What other potentials one may consider? One doesn't need to generalize very much. First, you have to require that the potential is a symmetric function, because you want to consider these gradients, and you don't want to do that in an oriented fashion. You don't want to think if it's phi v minus phi w or phi w minus phi v. But then you may think of any example that you'd like. For instance, u of x equals x to the 4th. That's a very natural example. Or more generally, absolute value of x to some alpha. That's also rather natural. Or you can think of something that you just draw, maybe like in a random walk, that we usually think of a simple random walk that has just plus minus 1 increments. So maybe you prefer increments of a certain kind. For instance, if you take a double well potential like that, maybe minus 1 and 1, you give a preference to these two values, and you prefer them over other values. Or an example which will feature later in the talk, you may take u of x to be 0 or infinity, 0 when absolute value of x is less than or equal 1, infinity when absolute value of x is more than 1. So the picture would look something like this. And people sometimes call this particular potential the hammock potential because it reminds a little bit of a hammock. And this example is perhaps a bit close to what we think about as in a simple random walk. A simple random walk would just have plus or minus increments. This is not in this framework. If I think of u as a function, it is somehow in the limit. But if you want something continuous, then this is some approximation. Each gradient is uniform on the minus 1, 1. And this is, in fact, easier. The other example with plus minus 1 increments is also very interesting, but more difficult. All right. So these are the examples. And what would one like to investigate? So as I said, one expects certain universality. If I consider a random walk like this, what will be the value? So my talk will focus on very simple characteristics. In particular, I'll talk about the variance of phi at the vertex nn. So I look at the value here at the corner. Let's think of the one-dimensional case. If I think of the value here at n, then we all know that the order of magnitude of this is typically square root of n. What would be the analogous fact in 2 dimensions? What would be the order of magnitude here? Well, it's not a priori clear. However, one does have the intuition that the fluctuations should be smaller, because in order to pull up a value, you have to pull up a larger neighborhood, so you get more constraints, more penalty, should be harder. Well, you might think that it's a power or something else. In fact, what is conjectured is that this should always be of order logarithmic in n. So this is conjectured. What is the basis of this? In the case that you have the potential x squared, you can do exact calculations. The distribution is Gaussian, and you get that. And then you imagine that there is some universality, which is not generally proven. Let me put up a picture. So if you can pull down the screen and put the picture. Does it work? Thank you. All right. So let me also mention regarding the hammock potential. I told you it's a uniform distribution of a kind. The u only takes 0 infinity values. You can put up the picture. So this distribution, if you think about it, it's a uniform distribution over all Lipschitz functions. So this is also a rather natural object, the uniform distribution on all possible Lipschitz functions, or uniform distribution on a convex polytope. Should I? Will that work? Okay. And here I've put up a picture of how this distribution looks like. So this is on a 100 by 100 grid, slightly different boundary conditions. This is in 2 dimensions, and this is in 3 dimensions, 1 slice. You can do this in any dimension. What you may see is that this guy doesn't fluctuate too much. The scale here is up to 3, and this is a 100 by 100 grid. It doesn't fluctuate much. Indeed, you only expect logarithmic variance, so square root log n fluctuation. However, what you may see is that it does have big islands where it goes down, or big islands where it goes up, even by a little, but still big islands. Whereas in 3 dimensions, it's very localized. There is only very small islands where it changes from height roughly 0. So there are definitely features to explore here. For instance, the level set is conjectured to have scaling limit of SLE4. The altogether scaling limit should be the Gaussian free field, and so on and so forth. Like in 1 dimension, you have Brownian motion limit. But all this is unknown in general. So I will speak about something which is known, but I will also tell about open questions. So maybe I'll take off the picture now, unless anyone has a question on it.
This was what potential?
This is with the hammock potential, which changes by at most 1 between neighbors. But supposedly, from where you're sitting, you wouldn't be able to distinguish that from the x squared potential. Supposedly, there is universality. From that distance, it should be the same picture. But this is unproven. You can take off the picture now. Thank you very much, and lift the board. Okay, so when are things understood? Let me say that there is one class of models which is a nicer class. This is when U is twice continuously differentiable. I write that as C2, twice continuously differentiable. And at any point x, U prime prime of x is less than or equal to some large constant and bigger or equal to some small constant, which is bigger than 0 and less than infinity. Let me call this class x squared like, because the x squared potential certainly satisfies this, and they are somehow similar to that. Then things are rather well understood. But for other classes, the situation is a bit poor. Let me exemplify that with another question. Yeah.
Are you just going to focus on rotationally symmetric potentials, or?
And potential is a one-dimensional function. It has to have u of x equal u of minus x. Otherwise, you don't know what you mean exactly by a gradient. But there's no other rotation, though, that you can apply. Yeah?
You said well understood. So what are the references?
For instance, Jason Miller's work, who received here the Rollo-Davidson Prize, he proved convergence of level lines to SLE4, and the scaling limit, the fact that it is Gaussian was known before that, I believe. Can't tell you precisely. And many other facts. I probably should have brought the list of references, but I cannot tell you exactly. Funaki and Spon may have been first, or one of the first to have good information on this class. Bertrand, probably you can correct me. No, okay, maybe Scott. All right, but there are a lot of works on this class. Okay, just to exemplify the situation for other models, so let me say that when I talk about showing that the variance is of order log n, I have in mind two things to show an upper bound of log n and the lower bound of log n. Regarding the upper bound, by this I mean that the variance of phi and n is less than some constant log n, then this is known mostly when u is again twice continuously differentiable, and the supremum over, the infimum over all x of the second derivative of u is positive. So u has a uniformly positive second derivative, and then an upper bound of this type is known, and this is by the so-called Braskamp-Lieb inequality. There are a few other cases. For instance, if your potential is absolute value x to the alpha, and alpha is between 1 and 2, if I'm not mistaken, the so-called infrared bound shows the boundedness. But just for an embarrassing open question, it is open when u of x is x to the fourth. And I think this situation is rather embarrassing, because x to the fourth might be the next thing you think of after x squared. In addition, you expect, because x to the 4 rises more quickly, it means you penalize more gradients which are larger. And we're trying to get an upper bound on the fluctuation, saying that you don't fluctuate too much. So maybe intuitively you expect it to fluctuate less than x squared. And this is open. It's open for a long time. So anyone here in the audience who's bored with the rest of the talk, this is a very nice question. I think it's solvable, and it's open. All right. So this is the poor situation of the upper bound. The lower bound is better understood. And in fact, my talk will also be on the lower bound. But I should say that it's better understood. So what about the lower bound? So again, there was work of Braskamp, Lieb, and Leibovich. This is from 75. And they showed that you have the lower bound when the supremum over x of u prime prime x is less than infinity. Or there was another possibility, or u is convex, plus some minor integrability condition, plus a small condition that is not so important. So they showed it for a large class, definitely a large class. There was also recent work of Joffe, Schlossman, and Velenik from, if I'm not mistaken, 2002, who managed to extend to approximations. So this is O2. They got approximations. What do I mean by that? That means that you have a potential U which is not very good, but it is very close to a potential U tilde which is very good. This difference is somehow, in the appropriate sense, small, and then manage to show that if you're a small perturbation of something in this class, then you're also good. And this was the first time that anybody proved a lower bound when the potential is not twice continuously differentiable, because you can be very close to a smooth potential, but yourself be, say, discontinuous. So this is a very nice work. All right, but it was mentioned in these works that the hammock potential case is still open, and other cases too. The double well case is still open. So for instance here, open hammock. And this is what my talk will focus about, the so-called hardcore constraints in the title. If you think about hammock, then you cannot fluctuate more than one. That's hardcore constraint. So I will speak about this work with Piotr, which is the following theorem. So we assume that the potential, somewhat mild conditions. So first you need some integrability conditions. These you can really think about as no conditions. You see that if you just define this as your density, if you take U, for instance, to be the constant zero function, then this will not be integrable. So you cannot define a measure with it. And you may impose a variety of conditions. We take the following. We could take something else, that the infimum of U of x is more than minus infinity, and the integral e to the minus U of x dx is between 0 and infinity. So this is just some technicality so that the measure is well defined. And after that, there is the main condition. So the main condition, so we are able to completely dispense of assumptions regarding the second derivative. We're able to show that suffices that the potential in our work be twice continuously differentiable. And it doesn't matter what it looks like, so anything you can draw, you can prove this for. And in fact, we believe, but haven't done, that with the Joffe-Schlossman-Velenik technique, you may extend this beyond smooth potentials. Or this does not include the hammock potential, or you may take that there exists some k between 0 and infinity, such that U is twice continuously differentiable on an interval, on the interval minus kk, and otherwise is infinite. And U of x is infinite when absolute value of x is larger than k. So this does include the hammock potential. And then the result is that the variance of the potential at nn is bigger or equal c log n. So this is a quantitative result telling you about the fluctuations, but before it was not known that the fluctuations go to infinity. And in fact, in 3 dimensions, the fluctuations are believed to be bounded, but there is no upper bound. So, so this you can see both quantitative and qualitative. And there are some, this is our main result. There are some other results of a similar flavor. I won't write them down, but let me mention that we have also a small ball, large deviation, and I should say and large deviation estimates. And maybe one result which I will write down, we also know that the probability that the maximum over x of, so maximum over v of phi v, what would you expect that to be? You see at the typical point the fluctuation is square root log n, but the maximum is bigger than that. And again, by analogy with the Gaussian free field, the maximum should go all the way up to log n. And we may show that, we can show that the maximum will be at least a constant log n with, say, probability 1/2. So these are, this is what we can prove. Okay. So let me, in the rest of my talk, tell you something about how this result is proved, something about the historical remarks, things have been known before. Any questions so far? Okay. Somebody ask a question?
Yes. You have the bound on the other side of the maximum, like a bit less than another constant times log n. Do you have a tail bound on the other side?
We do. We have something. We have. So first, if this is a half, so you're saying what is the chance that it will be log n to the 1 minus epsilon, so that this is very improbable? Yeah, we do. We have these large deviation estimates, and roughly to get the maximum, what you do, and we roughly are able to do that, maybe not quite as elegantly as in this picture, we take disjoint regions of space, and we're able to show that in each one of them there is a chance to reach this height, and that they're roughly in some sense independent, and hence you reach all the way to this height. But then in order for all of them to reach a much lower height, this would be exponential in something probability. So we're able to show that. But it's not, maybe here it looks very nice and promising, there are some details, and you know, it's not always as elegant as that. Other questions? Okay, so let me start to discuss a bit how these ideas go. And I should say that, and we also have similar results for other vertices. Here I wrote just NN, but this is for convenience. You can get what you need to get for the other vertices. So these ideas, these techniques of proving lower bound go back to Mermin and Wagner. So this is so-called Mermin-Wagner theorem from '66. Mermin and Wagner didn't prove such a thing, but they had some meta-principle. And the meta-principle says that if you have a two-dimensional system and it has a translational symmetry, here translating the surface up by a constant doesn't change the value summation u of the gradients, because the gradients don't change. If you have this translational symmetry, it shouldn't be broken in the limit. So this somehow shows that there is no limit, that you have delocalization. So this was an idea, and this idea was carried out in many implementations, which are then called Mermin-Wagner type arguments. And let me not write down the list of names, just mention here that it was Hohenberg and Braskamp-Lieb and Leibovich and Dobrushin and Schlossman and McBrien and Spencer in '77, Pfister in '81, Freulich-Spitzer, '81, Joffe, Schlossman, Welnick, 2002, and I will especially mention Richthammer from 2007. So in fact, what we do, we adapt the technique of Richthammer to this setting. Richthammer considered something else. He considered point processes in R squared, and he considered in particular the hard sphere model where 2 points cannot be too close, and proved translation invariance of Gibbs measures. And what we have is an adaptation of the technique to this setting and some extension of it, and there are some complications not there in the original one. Okay, let me now show you something, maybe the most interesting thing if you're not so interested in that. Let me show you the basic approach. And this basic approach, as I said, there are several flavors of it. McBrien and Spencer, Dobrushin and Schlossman. I will tell you the idea of Pfister, or roughly the idea of Pfister from '81. And if you've never seen this before, this is very nice. This is the most beautiful thing in the talk for sure. So I will explain to you how would you get a lower bound of log n if you had the most assumptions. So in particular, suppose your u is C2 of R, and the supremum over all x of u prime prime of x is less than infinity. How would you get now the variance of the lower bound? So we want that the variance of phi and n is bigger or equal to some constant log n. And Pfister found a very elegant way. So first let me put down one notation. Let me call d of phi, d for density, the density of my model, 1 over z, e to the minus sum v adjacent to w, u of phi v minus phi w. Okay, and now let me introduce one auxiliary function. So here is my torus, and here is the point 0, which is 0, 0. And I'd like to introduce an auxiliary function tau from the vertices of my torus to R, which is 0 at 0. And except for that, it satisfies the following condition. This is a deterministic function. The sum of all the gradients of tau, the sum tau v minus tau w squared, is less than or equal to, say, 1. Maybe it might be more convenient to write capital C here, so maybe 10 instead of 1. Well, under this assumption, there are many functions you could take. So this is bounded energy of a sort. And what I'd like is a function which is big at my target point. My target point is nn, and how big can I make my function there? Subject to this condition. And it is well known that it can be as big as square root log n. Let me give one particular suboptimal choice. You may take, but almost optimal, you may take tau to be log of 1 plus the L1 norm of v divided by square root log 2n plus 1. And one may check that this function satisfies this condition, satisfies that condition, and its value here at this vertex is exactly square root log 2n plus 1. So you reach value square root of log. And maybe there are other functions, but this is a nice expression to write down, so it's convenient. You can use any function which is big and satisfies these conditions. Okay, and now let me define, given a particular function phi, a particular configuration of my system, let me define two others. Phi plus is going to be phi plus tau. Phi minus is going to be phi minus tau. And now let me tell you a calculation, a simple calculation. I'm going to calculate, maybe here, the geometric average of the density at phi plus and the density of phi minus. Again, I'm emphasizing that I'm not thinking of anything random here. Phi is a fixed function, and I'm calculating the geometric average of these two quantities given by this expression. So the geometric average is just 1 over z, e to the minus 1/2, the sum over all edges, u of phi v plus minus phi w plus u of phi v minus phi w minus. But what is phi v minus phi w plus? Well, this is phi v minus phi w plus tau v minus tau w. And similarly here, just with minus of that. So when I have u of this difference, I can develop it in a Taylor expansion. U of phi v minus phi w plus tau v minus tau w by a Taylor expansion is u at the point phi v minus phi w plus u prime at the same point, phi v minus phi w, times this difference, tau v minus tau w. You should think of this difference as being small, because the sum of squares of all such differences is only a constant. So that's a very small perturbation. And then plus the second derivative at some intermediate point A of phi v minus phi w squared. So I take this Taylor expansion and I substitute it here. So this was, let's say, star, and I continue star over here. So star then equals 1 over... Say again? That's right, I do mean that. Thank you very much. Tau v minus tau w squared. Thank you very much. So let me substitute that in star. So what do I get? I get e to the minus. I have two contributions, u of phi v minus phi w. So I put that in. u of phi v minus phi w. The most important feature is that the first derivative has tau v minus tau w, but here it has the opposite expression, tau w minus tau v, and these two cancel. That's the most important thing. And then I remain with this one. And let me, instead of writing an equality, let me write an inequality. So this is bigger or equal to. And here I might instead put 1/2 the supremum over all x, u prime prime of x. And this multiplies tau v minus tau w, like so. So what have I obtained? Well, here, when I sum over all edges, I get at most a constant. This also is some constant. And this is exactly my original density. So I have obtained that this is bigger or equal to some constant times the density of the original function phi. This is the calculation of Pfister, a simple calculation. But what do I deduce from it? Well, intuitively speaking, I'm pretty much done. Because what do I see? Any function phi that you give me, it has some probability, or more precisely, some density. Now consider two other functions, one that lies above it, and the other lies below it, phi plus and phi minus. And this calculation tells you that the densities of phi plus and phi minus do not differ too much from the density of phi. Well, roughly it's an average, so one of them doesn't differ too much. So if this function is likely, then either that function or that function is likely. And this would be all that I require. So this is an inequality of densities. You can easily convert it by, say, a Cauchy-Schwarz inequality to an inequality of probabilities. So in particular, you may deduce the following. So you can deduce that for any, by a Cauchy-Schwarz calculation from that for any a bigger than 0, the probability that phi plus at nn differs from differs from tau of nn by more than a, times the probability that phi minus of nn, yes, sorry, I'm confusing it, sorry. The probability that phi plus at nn is less than or equal to a times the probability that phi minus at nn is less than or equal to a. The geometric average of these is bigger or equal to a constant times the probability that phi at nn is less than or equal to a, where now I do think of phi as a random function. So you sample phi randomly, you ask how close is it to 0, and that probability of being close to 0 cannot be much larger than the probability that the phi plus or phi minus is close to 0 at nn. But what is phi plus of nn? This is exactly phi of nn plus square root log 2n plus 1. And this is exactly phi of nn minus square root of log 2n plus 1. So if I think of where my probability lies, so I draw here where phi nn lies. So I have the a neighborhood of 0, and I have the a neighborhood of two other values, square root log 2n plus 1 and minus square root log 2n plus 1. And I see that whatever mass you put here, you have to put either here or there. And you also know that you're symmetric. So this allows you to conclude that your fluctuations are at least of height of order square root log n. So you conclude that the variance of phi nn is bigger or equal to c log n. So this is the argument of Pfister. Really, it's that calculation over there, and this is just one corollary you can draw from it. For any function, there is a function bigger and smaller which have roughly the same density. Okay. So this is one technique, Mermin-Wagner type argument, to show delocalization, to prove the lower bound. And what we would like to do is to adapt this technique to the hammock potential. So in the rest of my talk, let me focus only on the hammock potential. Other examples which we can treat follow in a very similar manner, so I don't want to get into additional technicalities. So I'd now like to exactly implement this argument for the hammock potential, but I cannot exactly implement it. What goes wrong? Maybe one of you, what goes wrong by trying to implement this argument for the hammock potential? Say again? The second derivative, right? It doesn't have, but where exactly does this manifest itself in the argument? Okay, Taylor, very good. Let me say it in different words. So when we're within the hammock potential, so now from the rest of my talk I only discuss hammock. So in the hammock case, this density d of phi is either 1 or 0, or maybe 1 over z or 0, according to whether phi is a Lipschitz function, according to phi Lipschitz or not. And what may happen when you try to create this phi plus from phi, so you're adding this tau, which has a very small difference on edges, but maybe you had a certain edge whose difference was very close to 1, 0.99. You raise this endpoint by an amount, and you raise this point by a slightly larger amount, and by doing so you created a slope which is 1.01, and immediately your density jumps from 1 over z to 0, and then you cannot make this comparison. This inequality no longer holds. So what may happen is that you add something small, but it breaks the Lipschitz property. And this is what you would like to avoid. And here comes this method of Richthammer, which we adapt to this case. So to overcome, and this was again in a different setting, but this was based on ideas of Richthammer, by replacing phi plus and phi minus by two functions, t plus of phi and t minus of phi, resembling the previous operation. So instead of adding tau, I look at my function, I consider its gradients, and I add something different in different places. In some intuitive sense, I will identify the problematic spots, the places where the gradient is close to 1. These places I'll just lift together, and other places I can make more of a fluctuation. Roughly, this is the idea, but there's subtleties in this, and Richthammer found a way to do it correctly, in particular in a bijective manner, in a continuous manner, as you will see. So now, what I would like to explain is how one would define these operations t plus and t minus. And let me first describe what properties they should have. So the desired properties. So first, my functions t plus and t minus, just like phi plus and phi minus, the previous operations, the operation of addition, will be bijections. So t plus, t minus, they take a function. I'm thinking of the Lipschitz case, but you can define it on any function. So they take a function and return a different function, and these are bijections. So already you see that you cannot simply take a problematic region and lift it together, and a different region lift in a different way, because when you look at the image, you will not know if a certain region was problematic to begin with or became problematic because you made changes to it. But there is a way to do it in a bijective manner. This is somehow one of the subtleties. The second property is that this function doesn't, what it does is roughly an addition. So t plus phi minus at the vertex v minus phi at the same vertex v, well, it adds something. It's bigger or equal to 0. but it doesn't add too much. It adds at most tau of v. So I still keep my function tau. This is what I'd like to add. The third property, which is what is required for hammock, is that it preserves Lipschitz functions. I'm only focusing on this case. You can write something more general for other cases. So it preserves Lipschitz functions. So it's not the operation of addition of tau, because it cannot break the slopes. If you just want these three properties, it's very easy. You can take t plus of phi to equal phi itself. If you don't do anything, then it satisfies these properties. So what I'd like to tell you next is that you sometimes do something. And what is it that you do? Well, the next property is that if, so there exists some delta bigger than 0, such that if phi is sampled with hammock potential, then with high probability, the change that you see in any particular vertex, tau plus phi at v minus phi of v, is at least what you want to see, tau v minus delta. So you're adding almost precisely delta. And it's clear that for the argument which I had here, it was not so important that I added exactly square root log n. Anything close to that would also do. So you have this property. And let me just mention that you have to say this with high probability. It's impossible to always add. Because if you think of the hammock potential case, there is a maximal function. You have the function which is highest at the point, because you can change by at most 1 between neighbors. So you have the function which is highest. And to that function, you cannot add anything. So this property cannot hold always, but we have it with high probability. And the last property, which you need, but is somewhat hidden in the passage from densities to probabilities, is that when you do this, you have to not distort space too much. So you have a control and even an explicit formula for the Jacobian of this function t plus. So if you just added tau, t plus and t minus, say. If you just added tau, you would not distort space at all, and this distorts only a little. And I've focused here on t plus. This is because t minus just subtracts what t plus adds. So I'm going to take phi v minus t plus phi v to equal t plus phi minus phi v. So in this sense, it's also a bit like addition and subtraction. So these properties go through. OK, this is what I'd like. And now the question is how to achieve it. So I won't have time to tell you in full detail how you achieve it on the two-dimensional grid. But let me explain to you how you would achieve it on the one-dimensional grid, which is much easier. And then I will explain how you change this to the two-dimensional grid with somewhat less detail. But the one-dimensional grid already contains many of the essential ideas. OK, so now I consider the one-dimensional case. And I take my lattice, my one-dimensional lattice, from 0 to n. In the one-dimensional case, the analogous quantity to the function tau, which was on the board before, is the function tau that at the point I equals I divided by square root n. So this function adds square root n here, and the sum of gradients squared is at most 1. Is actually exactly 1. OK, so what I'd like to define to you, define inductively how much you add. So Si is going to be t plus phi at the point I minus phi of I. And I'll first take S of 0 to equal 0. And now I'd like to define to you inductively how much you add to a point. So I'd like to tell you what is Si. So I'll take Si to be a function of the following things. I want to know how much I added to the previous vertex, one previous in the chain. I'd like to know how much I'd like to add to this vertex. And I'd like to know the difference between the value of the function at this vertex and the value of the function at the previous vertex before adding anything. So just to give a picture, I have my vertex I minus 1. I have my vertex I. My function is at a certain height, phi I minus 1, and at a different height, phi I here. This point has been pushed up by a certain amount, si minus 1, and I now need to determine by how much to push this point up. I'd like to push it up all the way by tau of I, and then if my previous slope was this, my new slope would become this. But the actual amount which I push it up by is a function of the previous slope, how much I added, and how much I'd like to add. Okay? And which function is that? It's the following function. Here, I put phi I minus phi I minus 1. So this is a quantity between minus 1 and 1 in the hammock case. And at the very edges, when the slope is exactly 1 or minus 1, I'm going to add si minus 1. So if your slope was almost 1, you just add the same value. If, on the other hand, you're away from 1, then you add what you want to add. You add tau of I. And in the middle, in the intermediate region, you just connect it by straight lines. And what do I mean by intermediate regions? For this construction, you fix some epsilon, maybe 0.9, maybe 1 minus epsilon, fixed, independent of everything. So maybe 0.1, and that's your threshold for going between the two behaviors. There is one technical detail which I'm sweeping under the rug here. I will also require that this slope requires slope to be less than 1. And if this is not the case, then reduce this height until this is the case. So you don't actually add tau, you add something a bit less. In some sense, this never happens, so I don't. It happens, but with very low probability, so I won't focus on that. Okay, so this is how much I choose to add to the next vertex. I look at what I added to the previous one. Generally, I'd like to add tau I, but if I cannot, then in a linear, continuous fashion, I add less and less. This is what happens until I add what I added to the previous one. And then the fact to notice is that this is an invertible operation. How do you see that this is invertible? Well, it really is based only on the following simple calculus fact, that if you have a function g from R to R, whose second derivative is bounded above by 1, strictly less than 1, then the mapping x goes to x plus g of x is a bijection. R to R, from R to R. Maybe from R to R. So where does this function, where do I find this function here? I remind you that Si is, well, it's given above. It's what I add. So G is this F. It's what I add. And this is invertible because my slope is at most 1. So if I know everything that happened up to position I minus 1, and I'd like to recover my initial value for I, then I just have to ask myself how much I added, and then I may use this fact, and it will be invertible. And this is a simple calculus fact. So this is the construction in the one-dimensional case. All right? Questions? Okay. And now let me ask what can go wrong. So I'd like to say in the one-dimensional case that to the last value here, I'm adding roughly square root of n, roughly tau of n. What can go wrong? In which situations will this not be the case? What can go wrong is that I land many times in this region, in the 1 minus epsilon region. So maybe my initial function, which is generally nice, had some region where it had near maximal slopes. So these are extremal slopes, meaning that they have slope more than 1 minus epsilon. Extremal slopes, which means bigger or equal to 1 minus epsilon. If I have a long stretch of such, then each one makes me add less, and it is possible that at the end of the day I will not add as much as I wanted. So we want to avoid long intervals of bigger or equal to 1 minus epsilon gradients or slopes. Okay, and let me now go to the two-dimensional case. How do you adapt this construction to the two-dimensional case? Well, when you do that, you have one difficulty you have to cope with. In the two-dimensional case, there is no linear ordering of the vertices. So who is the next vertex to treat? Here it was very clear. So in the two-dimensional case, there is a modification. The order of the vertices, depends on phi. And in fact, you may even jump around. So it is possible that you first treat, say, this vertex, and then that vertex, and then this vertex, but then suddenly some vertex here, and then perhaps this vertex, and then that, and so on. How do you choose your next vertex to treat? Well, to each vertex that you are considering now, so maybe you think this vertex will be the next. What do? You look at all its previously treated neighbors. So first of all, your default to vertex v is to add tau of v. But it is possible that your previous neighbors tell you to add less because of this recipe. So for each vertex v, you consider previously treated neighbors w, and you apply the above recipe. And they might reduce you from tau of v to some smaller quantity. If you have several neighbors which have been treated, w and u, you apply this recipe to each, and each one reduces you. So at the end of the day, each vertex v has a new quantity, which is what you will add if he is the next, which is the minimal according to all his neighbors. Each one reduces. Then you pick that vertex in the whole square, which has the minimal of all of them, and that's what you add. You add to that vertex the value which is determined by its previously treated neighbors. So if your tau function is very small somewhere, maybe you'd start there. And if it's big somewhere else, you might get there late. So the ordering depends on the vertices. And except for that, it is the same. But one has to think, why is this new recipe invertible? This is not obvious. And again, this is somehow an adaptation of what was done in Richthammer's work, where some recipe of this kind was also used. It was in the continuum, it was a bit different, but the same basic thing. And again, what do you want to avoid? Want to avoid regions of high gradient, larger or equal to 1 minus epsilon. What does it mean avoid? These may or may not exist. What you want to show is that they don't exist with high probability. So this is what's written here, that with high probability you add. This high probability regards the regions that have gradient bigger or equal to 1 minus epsilon. You want them not to be too numerous. Now this, I would think that this property is obvious. So this means let us mark edges along my grid where my random function happened to be bigger or equal to 1 minus epsilon. And I'm sampling my function uniformly from all Lipschitz functions. So I would think that it is obvious that this set of edges does not, say, percolate, does not have a very large component, is subcritical. If I am allowed to take epsilon as small as I'd like, then the probability that you see a long stretch of such edges is exponentially small in the stretch. Well, this is not obvious. This is actually a difficult point. Controlling the set of extremal gradients, proving that if you choose epsilon to be 0.001, then they don't percolate, that you have bounds on their size, is difficult. And we're able to overcome that using reflection positivity, so-called chessboard estimate. But this is a suboptimal solution. Those of you who know it may know that it restricts us to work on the torus. It restricts in several ways, and we'd like to get rid of it. So if you have some nice idea how to do this, and more generally, not just for the hammock potential, we now think maybe we know how to do it for the hammock, but more generally, when you sample with some other potential, even x to the fourth, you want to know that gradients of a very large size do not percolate. That would be very helpful. It's not obvious, although it seems that it should be. It just isn't. This same property is what is required to have the good estimate on the Jacobian, so I'm not saying more about that. Okay, so with that, I'm done describing the construction, and the result follows from it. Let me finish by telling you some open problems. So open. So first there is this getting rid of reflection positivity. This would be nice. We think we might know something when it's hammock potential, but not in other cases. Next thing, to get an upper bound. So I've already told you that this is a very embarrassing question. Next thing, if you're more ambitious, the scaling limit to show that it goes to a Gaussian free field, it's expected to be universal, like Brownian motion in one dimension. And yet another thing, well, you might like to improve our theorems to a larger class of functions. This we might be able to do with the Joffe-Schlossman-Welanik technique. But here is some functions we cannot treat. Integer valued functions. And this is a very interesting class. I mentioned briefly in the beginning. What is the generalization of simple random walk? This is a function on the two-dimensional grid, all of whose gradients are exactly 1 or -1. Uniformly sample from the collection of all such functions. That's an important model. It's equivalent to so-called square ice, a uniform 6-vertex model, also equivalent to proper 3 colorings of the two-dimensional lattice. Nothing is known about this model. So you fix the value to be 0 in the center. What is the fluctuation in the corner? It's expected to be square root log n. It's not known that it's less than n, like in the one-dimensional case. This is, by the way, the only bound known also for x to the fourth potential. And it's not known that it goes to infinity. Nothing is known about it. And it's a very nice model, and would be nice to do something. There is something about average decay of correlation by Eisenman. In this case, by Pinson, actually. Okay, and I'd love to do something in general about these integer valued models. There are only one result in the literature by Freundlich and Spencer. In the case of absolute value x and x squared, they show delocalization. One result of the delocalization kind, and nothing else. Okay, thank you very much. Nathaniel?
So, I mean, this story about the reflection positivity, I mean, if the big gradients did percolate, couldn't you say that somehow then the fluctuations would be much, much higher?
Maybe they percolate in the sense of going up, going down, going up, going down.
Then you have
maybe, yeah. It's not completely obvious, but maybe. But we don't have an upper bound on the fluctuations.
But you would get a lower bound.
Not by this technique, so you'd have to think exactly how, because again, maybe they cancel each other. Exactly, maybe 1 minus epsilon, 1, maybe 1 minus epsilon minus 1 plus epsilon. And exactly cancel. It doesn't immediately imply to be big, just maybe seems natural.
Right, well, if there are no further questions, let's thank Ron again.